I want you to try a little experiment with me. Wherever you are right now, maybe you're sitting in a library, maybe you're commuting on the metro, or maybe you're just lying in bed.
Hmm.
I want you to visualize the ground beneath you.
Mm.
It feels solid, doesn't it?
Yeah.
It feels permanent. You put a cup of coffee on a table, and it stays there. You build a house, and you expect the foundation to stay put.
It's probably the ultimate illusion of human existence. I mean, we live our lives on this timescale of minutes, days, and years, but the Earth...
Totally different scale.
Oh, completely. The Earth operates on a timescale of millions and millions of years. And on that timescale, that solid ground beneath your feet is about as stable as, I don't know, a raft on a choppy river.
Exactly. We aren't just spinning in space. The actual surface of our planet is, so the crazy part, it's tearing itself apart, crashing together, and recycling itself.
Constantly.
And that movement, that slow, grinding, relentless drift, is the topic of today's deep dive.
And this isn't just any deep dive, is it? We have a very specific mission today.
We do. Welcome back to the deep dive. Today we are focusing on a full summary for UPSC, and this is brought to you by the Simplified UPSC by PPP YouTube channel.
It's great to be back. And yeah, the goal today is laser focused. We are going to master the NCERT Class 11 fundamentals of physical geography, specifically Chapter 4.
That's the one. The chapter titled Distribution of Oceans and Continents. Now, I know what you're thinking. I've read the NCERT. I know the continents move. But we're doing this differently. We aren't just summarizing the text. We're doing a strategic breakdown with PYQ linkage. That's previous year questions, of course, derived from actual exam papers. We're looking at 2014, 2020, and even the 2025 paper.
And this is so valuable because, let's be honest, reading the chapter is passive. It's one thing to read it, but understanding how to use that theory to construct a high-scoring answer for General Studies Paper 1, that's a whole different skill.
It's an active skill.
Exactly. We're going to try and bridge that gap between just knowing the information and actually applying it.
Absolutely. We are going to turn you into a tectonic expert by the end of this hour. But before we jump into the shifting sands of time, I have a humble request for you. If you want to boost your retention and keep getting these deep dives, please subscribe to the Simplified UPSC by PPP channel. It really helps the algorithm get this content out to serious aspirants like you.
And if you are capable and you find value in what we do, if this content helps you save time and understand things a bit better, please consider supporting us on Patreon. That support is what allows the team to keep the lights on, do the research, and frankly, keep creating this super useful content.
And a massive, heartfelt shout out to all our current supporters.
Yeah.
You guys make this possible. Also, don't forget to like the video and leave a valuable comment. Let us know what clicked for you or maybe what you want us to cover next.
Oh, and one last resource alert before we dive in. You don't have to frantically take notes while you're listening. We know you might be driving or working out or something. Free notes with practice PYQs are available on the public Telegram channel.
However, if you want the VIP treatment, I'm talking access to all the videos in this series at once. Organized premium notes, which include detailed breakdowns, extra PYQs, and crucially, model mains answers for the questions we are going to discuss later.
Which is the key part.
It is. You need to get into the private Telegram library. Just DM us on the public Telegram channel to join.
See?
Okay. Logistics done. Let's drift.
Let's do it. Let's drift.
So the core mystery we are solving today is simple, but it's actually really profound. How did the continents get where they are? Because if you look at a world map, really look at it, it looks suspicious.
It really does. It looks like a jigsaw puzzle that someone just scattered across a blue table.
And for a long time, centuries, actually, that observation was just dismissed. People thought, oh, that's just a coincidence. Today, we are going to trace the journey from that coincidence to scientific fact. We're going from Alfred Wegener's preposterous idea to the high-tech evidence of seafloor spreading, and finally to the unifying theory of plate tectonics.
And it's such a great story of how science actually works. It starts with an observation, then it faces total rejection, it has to wait for better technology, and then finally it arrives at a theory that just explains everything.
Let's start with the man who kicked it all off. Section 1, the jigsaw puzzle and the continental drift theory. The year is 1912. The man is Alfred Wegener. Now, here's the kicker. He wasn't a geologist, was he?
No, not at all. And that's a huge part of the story. Wegener was a German meteorologist, a weather guy.
A weather guy?
Yeah, he studied the atmosphere, polar air circulation, things like that. And in the scientific community of the early 20th century, disciplines were very, very siloed. So a meteorologist telling geologists how the Earth works was like a plumber telling a surgeon how to operate.
He was stepping on a lot of toes.
Oh, big time. But because he was an outsider, he noted the things that, maybe the rock guys missed. He was looking at climate data in the rock record, which was a bit of a different perspective.
And he wasn't the very first person to notice the shapes, though.
That's correct. As far back as 1596, a Dutch map maker named Abraham Ortelius suggested the Americas were torn away from Europe and Africa.
Wow, 1596.
Yeah. And later, Antonio Pellegrini even drew maps showing the continents all joined together. But these were just sketches, ideas, hunches. Wegener was different because he didn't just have a hunch, he built a case file, a proper scientific case.
He put together the Continental Drift theory. So let's look at the world according to Wegener. What was his core hypothesis?
Well, Wegener proposed that the Earth didn't always look like it does today. If you could rewind the clock roughly 200 million years, there were no separate continents. No America, no Africa, no Asia. There was just one massive supercontinent.
One giant island floating in a global ocean.
Exactly. He called it Pangea. The word comes from Greek pan, meaning entire, and gai, meaning earth. So all Earth.
And if there is only one island, there must be only one ocean surrounding it. That makes sense.
Right. He called that panthalassa, which means all water. Wegener argued that around 200 million years ago, this massive block began to break apart. It was a divorce of continental proportions.
A very messy divorce.
A very messy one. First, it broke into two large chunks, Laurasia in the north and Gondwanaland in the south.
Gondwanaland. It sounds like something out of a fantasy novel, but it's incredibly important for our listeners, especially those in India.
It is. Gondwanaland was the motherland, so to speak. It eventually fragmented to become South America, Africa, Australia, Antarctica, and, crucially for our discussion, the Indian subcontinent.
In Laurasia, the northern block, that became North America and Eurasia.
Correct.
Okay, so that's the narrative.
Yeah.
A supercontinent splits up and the pieces drift away. But in science, a cool story isn't enough. You need proof. You need receipts. And Wegener brought what I like to call the files.
Ah, I like that. The files.
Let's walk through the 5 key pieces of evidence he presented. And this is prime material for prelims, by the way. You really need to know these.
Absolutely. So let's start with evidence number 1, the matching of continents, or what he called the jigsaw fit.
This is the one we all notice in school. The bulge of Brazil fits almost perfectly into the curve of Africa.
Specifically, the Gulf of Guinea. It's remarkably precise. Now, Wegener's critics at the time, they said, look, coastlines erode, waves crash against them, rivers dump sediment. The shape changes literally every year. A fit like that is just accidental.
Which, to be fair, is a decent point. Coastlines do change constantly.
They do. It's a valid criticism. But the real rebuttal came much later, in 1964. A scientist named Bullard basically shut that argument down for good. He used a computer program, which was pretty advanced for the 60s.
I was going to say a computer in 64.
Yeah, exactly. He used it to fit the Atlantic margin. But, and this is the key point, he didn't use the coastline. He used the 1,000 fathom line.
Can you explain that distinction? What's the 1,000 fathom line?
Sure. So the coastline is where the water meets the land today. But the continent itself actually extends underwater for quite a way. That's the continental shelf. The 1,000 fathom line is deep underwater, near the true edge of that continental block.
Ah.
So erosion affects the beach, sure, but it doesn't really affect the deep shelf edge thousands of feet down.
Oh, it's the real shape of the continent. And when Bullard mashed them at that depth.
It was what he called a quite perfect match. It wasn't just a coincidence. It was a precise, undeniable geometrical fit.
Okay, so the shapes fit. But shapes can be deceiving. What about the substance, the stuff the continents are made of? That brings us to evidence number 2. Rocks of the same age across oceans.
This is where radiometric dating became Wegener's best friend, or would have if he'd lived to see it perfected. Scientists found a belt of ancient rocks. We're talking 2,000 million years old.
2 billion years old.
2 billion, yeah.
Yeah.
Along the coast of Brazil. And then they hopped across the Atlantic to Western Africa and found the exact same belt, same age, same composition.
It's like finding a torn photograph where the image lines up perfectly across the tear. There's no other explanation.
Precisely. And there's another little detail here that is often asked in exams. The earliest marine deposits, which is basically the first evitas of an ocean existing between them, are from the Jurassic Age.
So any rocks older than the Jurassic period show no ocean.
Exactly, which strongly suggests that before the Jurassic period, the Atlantic Ocean simply didn't exist. The land was continuous.
Okay, this is building a strong case.
Ugh.
Let's move to evidence number 3.
Ugh.
This one is my favorite because it deals with these crazy climate paradoxes. Teallite.
Yes, teallite. So for the non-geologists listening, teallite is a specific type of sedimentary rock that's formed out of glacier deposits.
Right.
When glaciers move, they act like giant bulldozers. They grind up rock into this fine paste and mix it with huge boulders. When the ice finally melts, all that messy debris hardens into a very distinct rock called teallite.
So if you find teallite, you know for a fact a glacier was there at some point.
You know it. Now, here's the puzzle. We find the Gondwana system of sediments, which has these thick layers of teallite at the base in places that are currently tropical or subtropical. We find them in India, we find them in Africa, Madagascar, Australia.
Wait. So you're saying India, which is hot, humid, tropical in many parts, has rocks that can only form under massive sheets of ice.
Yes, and not just India, Central Africa too. This proves that all these now separate landmasses, India, Africa, Antarctica, Australia, must have had similar histories and, crucially, similar paleoclimates.
And the only way they could all be covered in a giant ice sheet at the same time is
If they were all clumped together down near the South Pole. I mean, you can't have a continental-scale glacier in modern-day Chennai unless Chennai used to be where Antarctica is today.
That is just, it's undeniable, isn't it?
Yeah.
It's hard to argue with a rock that says, I was made in the ice when you're standing in the jungle.
It really is.
Okay, evidence number 4. Placer deposits. This one feels like a detective story. A geological whodunit.
It really is. So let's look at Ghana on the West African coast. Ghana has these huge, rich deposits of gold, alluvial gold. People have been mining gold there for centuries.
Right.
But here's the geological mystery. Usually, placer gold like that erodes from a source rock, a vein of gold up in the mountains.
In a mother lode.
Exactly. You need the source. But in Ghana, there is no source rock. The gold is there in the riverbeds, but the veins it should have come from are completely missing.
So where did the gold come from? It didn't just appear out of nowhere.
It came from Brazil. The gold-bearing veins, the mother lode, are found in the Brazil Plateau.
No way.
Yes. When the continents were side by side, the gold eroded from the mountains in Brazil and was deposited by rivers into the deltas that would one day become Ghana. Then the continents split.
So Brazil kept the bank vault, the veins, and Ghana walked away with all the cash, the deposits.
That's a perfect analogy. Brazil kept the source, Ghana kept the placer deposits. It's pretty much irrefutable proof they were once linked.
Okay, this case is getting stronger and stronger. The final piece of evidence from Wegener's file, the distribution of fossils.
This one is great because it helps disprove the alternative theories that were floating around at the time. Take the lemur, for instance. It's a small primate. Fossils are found in India, Madagascar, and Africa.
So before drift theory, how on earth did people explain that? Did they think lemurs were excellent swimmers?
They couldn't explain it, so they scratched their heads and invented a hypothetical land bridge called Lemuria.
Lemuria?
Yeah, a land bridge that supposedly connected India and Africa and then just conveniently sank into the sea without a trace.
Which sounds like Atlantis nonsense, pure fantasy.
It was scientific desperation, but Continental Drift explains it simply. There was no ocean to cross, they were all on the same landmass, the lemurs just walked.
And then there's the Mesosaurus, the big one.
Oh, yes, the Mesosaurus. This is the smoking gun for the fossil evidence. Mesosaurus was a small, freshwater reptile, and crucially, it was adapted to shallow, brackish water. It was not a deep ocean swimmer. It absolutely could not have crossed the Atlantic.
Yet we find its skeletons. Where?
Only in 2 places on the entire planet, the Southern Cape Province of South Africa and the River formations in Brazil. Those 2 places are now separated by 4,800 kilometers of deep ocean.
So unless the Mesosaurus built a little reptile boat, the land must have been connected.
There is no other logical conclusion.
The Wegener lays all this out. The shapes fit, the rocks match, the ancient climates match, the gold deposits match, the fossils match. Seems like a slam dunk case.
Yeah.
But he failed. The scientific community didn't just reject him, they mocked him. They were vicious. Why?
And that brings us to section 2, the mechanism problem. Because, you see, in science, observation is only half the battle. You can have all the evidence in the world, but you need a mechanism. You need to explain how it happens. Wegener had the what, but he got the how completely and spectacularly wrong.
He had to explain what force could possibly be strong enough to push a massive continent, a block of granite, through the solid ocean floor. That's a huge ask.
It's a huge ask. And his explanations were, well, they were weak. He suggested two forces. First, the pole fleeing force. This relates to the Earth's rotation and the fact that it bulges at the equator. He thought the spin of the Earth was kind of flinging the continents toward the equator.
Okay. And the second force?
The tidal force, the gravitational attraction of the moon and the sun that pulls the tides. He thought this constant tugging was dragging the continents westward.
And the physicists of the day, they just had to crunch the numbers on that, right?
Oh, they did. A very famous geophysicist, Harold Jeffreys, calculated that for the tidal force to be strong enough to move a continent, it would have to be so mind-bogglingly powerful that it would stop the Earth's rotation completely within a single year.
Ouch. So not even close.
Not even in the same universe. The forces he proposed were totally, laughably inadequate. So despite all that beautiful evidence, the theory stalled. The files were put in the basement and gathered dust for decades.
And it stayed in that basement till after World War II. This is the turning point in the story. What changed?
Technology changed, specifically military technology. War, for all its horrors, drives innovation. During the war, navies on both sides needed to map the ocean floor in detail to hunt for submarines.
Ah, sonar.
Exactly. And after the war, we started laying transoceanic telegraph cables. So for the first time in human history, we had a detailed picture of the ocean floor.
Before this, what did people think the ocean floor even looked like?
Most scientists assumed it was a flat, boring, featureless bowl, just a deep basin collecting mud for billions of years.
And it turns out.
It turns out the ocean floor is the most dramatic and geologically active landscape on the entire planet. They found the Mid-Oceanic ridges, the longest mountain chains on Earth, all entirely submerged.
The longest mountain range on Earth is underwater. That's amazing.
It is. They found deep trenches that plunged down 11 kilometers, deeper than Everest is high. They found thousands of active volcanoes. The ocean floor was alive.
So this new data revived the discussion about drift, but they still needed a plausible mechanism, a new engine. Enter Arthur Holmes and his convection current theory.
Right. Now, Holmes had actually proposed this way back in the 1930s, but nobody really paid attention until this new ocean data came in. He suggested that deep inside the Earth's mantle, there are radioactive elements decaying and generating a massive amount of heat.
Like a nuclear reactor at the center of the Earth.
In a way, yes. And this heat causes the semi-molten rock of the mantle to move. It creates currents.
Like boiling a pot of soup. The hot stuff rises and the cooler stuff sinks.
Exactly like that. Hot material rises, it hits the bottom of the crust, spreads out, cools down, and then sinks again, creating these huge, slow-moving circular currents. Holmes said these currents are the engine. The continents aren't plowing through the ocean floor like Wegener thought. They are riding on top of these currents like a conveyor belt.
Which brings us perfectly to Section 3, seafloor spreading. This is the concept that really tied it all together. The man is Harry Hess. The year is 1961. And this is crucial for our listeners because seafloor spreading is a very frequent topic in exams.
It is absolutely foundational. Hess looked at all the new data from the Mid-Oceanic ridges. He saw that these underwater mountains were sites of huge volcanic eruptions. And he proposed a bold, brilliant hypothesis. The ocean floor itself is pulling apart at these ridges.
Pulling apart, not crashing together.
Pulling apart. He said the ridge is essentially a giant crack in the Earth's crust. New lava, or magma, rushes up from the mantle, wedges itself into that crack, solidifies into new rock, and in doing so, it pushes the old crust apart. The floor literally spreads.
So the Atlantic Ocean is literally getting wider as we speak.
It is. About at the same speed your fingernails grow. A few centimeters a year.
Wow. Now, Hess didn't just guess this. He had hard data, right? Let's list the evidence for spreading, because this is exactly what you need to write in your exam answers.
Right. Let's break it down point by point. Point 1 is the most obvious. The volcanic activity. It's incredibly common all along the mid-oceanic ridges. It proves the crust is thin and is rupturing there.
Okay, that makes sense. What's point 2?
Point 2. Rock similarities. This is fascinating. If you take a rock sample from the very crest of the ridge, and then you sail 100 kilometers to the east and pick up another rock, and then you go back and sail 100 kilometers to the west and pick up a rock, those two rocks, the one from the east and the one from the west, are identical.
Identical in what way? Like they look the same?
Identical in every measurable way. Their chemical composition, their magnetic properties, and most importantly, their age. It's a perfect mirror image. The ridge is the mirror, and the floor on both sides matches perfectly as it spreads out.
Okay, that's powerful. What's point 3?
Point 3 is the age gradient. Rocks right at the ridge crest are brand new, literally 0 years old, still cooling down. But as you move away from the ridge in either direction, the rocks get progressively and predictably older.
And point 4 is the one that really shocked everyone, right? The huge difference between the age of the oceanic crust and the continental crust.
This is a statistic you must memorize for the exam. The oldest rocks we've ever found on land on the continents are up to 3,200 million years old. 3.2 billion years. Ancient. But the oldest rock ever found on the entire ocean floor, it's only about 200 million years old.
That is a staggering difference. The continents are ancient grandparents. The ocean floor is a toddler.
Exactly. And that's the killer proof that the ocean floor is not a permanent feature. It's constantly being created and, as we'll see, destroyed. It doesn't last long, geologically speaking.
So that leads to point 5, sediment thickness.
Right. Think about it. If the ocean floor was billions of years old, it should be covered in miles and miles of dust and sediment that has settled over eons. But it's not. Near the ridges, the volcanic rock is bare, it's clean. The sediment only gets thick when you get very far away from the ridge on the older parts of the crust. This confirms that the floor near the ridge is young.
But wait, I have a question. If the ocean floor is constantly being created at these ridges and spreading out, shouldn't the Earth be getting bigger? Like a balloon that's constantly being inflated.
That's the logical question, isn't it? It's the consumption problem. And Hess solved this too. He said, the crust is created at the ridges, it spreads out, and then it sinks back down into the mantle at the oceanic trenches.
The deep parts they found.
The very deep parts, the crust gets subducted.
Subducted means?
It means it's forced downwards, pushed back down into the hot mantle to be melted and recycled. So it's a perfect system.
Yeah.
Created at the ridge, destroyed at the trench, the Earth stays the same size.
A planetary scale recycling system. Which leads us perfectly to the grand finale. Section 4. Plate Tectonics, the Unifying Theory. Yeah. This is 1967. Mackenzie, Parker, Morgan. This is the modern Estonian model. So how is plate tectonics different from Wegener's continental drift?
This is probably the most common confusion students have, and it's a critical distinction. Wegener thought the continents moved. He pictured them as ships plowing through a static ocean floor. Plate tectonics says, no, that's wrong. The lithosphere moves. The lithosphere is the rigid outer layer of the Earth. It's the crust plus the solid top part of the mantle. And this lithosphere is broken into massive, irregularly shaped slabs called plates.
So the plate can carry a continent, or it can carry a piece of ocean floor, or sometimes both.
Exactly. It's not the South American continent that's moving. It's the South American plate that's moving. And that plate includes the continent of South America and about half of the Atlantic Ocean floor attached to it.
And what are these plates floating on or moving over?
They move horizontally over the asthenosphere. That's the hotter, weaker, semi-molten, plastic-like layer in the upper mantle. You can think of it like giant, rigid slabs of ice moving over a layer of thick, viscous honey.
Let's run through the roster then. There are 7 major plates. This is standard geography, but it's essential to know them.
Right, let's list them quickly. First, the Antarctica plate, which includes the continent and the surrounding ocean. Then you have the North American plate and the South American plate. Then there's the massive Pacific plate. Now, it's important to note this. The Pacific plate is almost entirely oceanic crust. It has very little land on it.
Okay.
Then you have the India, Australia, New Zealand plate. They're all on one plate. Number 6 is the Africa plate. And number 7 is the Eurasia plate.
And then we have the minor plates. And these are favorite targets for prelims. Match the column questions, so you need to know where these are. I'm going to name a plate. You tell me where to find it on a map.
Let's do it.
The Cocos plate.
That's a small but important one. It's sandwiched between Central America and the Pacific plate. It's diving under Mexico and Central America.
Okay. The Nazca plate.
That one is between South America and the Pacific plate. Think off the coast of Peru and Chile. This is the plate that is currently crashing into South America to form the Andes Mountains.
The Arabian plate.
That's basically the Saudi Arabian landmass. It's breaking away from Africa, creating the Red Sea.
The Philippine plate.
That's an oceanic plate between the Asiatic mainland and the Pacific plate. A lot of activity there.
Carolina plate.
That one's a bit more obscure. It's just north of New Guinea, right between the Philippine and the Indian plates.
And finally, the Fuji plate.
That's a tiny one, northeast of Australia.
Got it. So this map of plates is not static. The movement isn't random. The plates interact at their edges, We call these boundaries, and there are three main types.
Yes, this is the core of tectonics. Type 1, divergent boundaries. This is where the plates pull away from each other. New crust is generated here from rising magma. These are the spreading sites.
The Mid-Atlantic Ridge being the classic example.
The classic example.
Okay, type 2.
Type 2, convergent boundaries. This is where plates crash into each other. One plate usually dives under the other in a process we've mentioned. Subduction. Crust is destroyed here. This is where you get the deep trenches, the big earthquakes, and the explosive volcanoes.
And type 3.
Type 3, transform boundaries. This is where plates slide horizontally past each other. Crust isn't produced or destroyed, it just grinds along.
Give me a famous example of a transform boundary.
The San Andreas Fault in California. That's the boundary between the Pacific Plate and the North American Plate. The Pacific Plate is sliding northwest past North America. And that's why California has so many earthquakes, but not really any volcanoes in that specific area. No subduction, no magma.
That makes sense. And these plates, I know we said they move at the speed of fingernail growth, but how fast are we actually talking?
Well, it varies a lot. The Arctic Ridge is the slowpoke of the group. It's spreading at less than 2.5 centimeters a year, slower than your fingernails grow. But the East Pacific Rise, off the coast of South America, is a real speed demon. It's moving at over 15 centimeters a year.
Okay, let's bring this whole story home. Section 5, the Indian Plate. For our listeners in India, this is our geological biography. We weren't always a part of Asia.
Oh, not even close. If you rewind the clock about 140 million years, the landmass that would become India was way down south, around 50 degrees south latitude. We were practically neighbors with Antarctica and Australia.
So we embarked on a massive geological road trip north.
A very fast road trip, geologically speaking. India broke off from the supercontinent of Gondwanaland and started racing north toward the Eurasian plate at a very high speed. But between India and Eurasia, there was a massive body of water.
The Tethys Sea. I remember this from school.
Correct, the ancient Tethys Sea. And as India moved north, the floor of the Tethys Sea was being subducted or pushed under the southern edge of Asia.
And something huge happened on the way up, right? 60 million years ago? Something that shaped modern India.
Yes, the Deccan Traps event. This is absolutely crucial for Indian geography. As the Indian plate was moving north, it passed over a hotspot, the Reunion hotspot. You can imagine a stationary blowtorch sitting in the mantle, and the Indian plate just moved right over the top of it.
And the blowtorch burned a hole right through the plate.
Essentially, yes. It caused a massive, massive outpouring of fluid basaltic lava that covered huge parts of peninsular India. That's why we have the distinctive black soil and the steppe-like basaltic rocks in Maharashtra and the Deccan region today. It's basically the scar tissue from that hotspot encounter.
And then the main event, the crash.
Roughly 40 to 50 million years ago, India collided with Asia. The Tethys Sea, which had been shrinking, was finally squeezed out of existence. All the sedimentary rocks that were lying at the bottom of the Tethys Sea, billions of tons of sand and mud, were caught in the vise.
And they had nowhere to go but up.
Nowhere to go but up. They were buckled, folded, and thrust thousands of meters into the sky.
And those folded, fossil-filled sea-bottom rocks became
the Himalayas. The highest mountain range in the world is literally the fossilized bottom of an ancient sea.
And it's not over, is it? The crash is still happening.
No, not at all. The Indian plate is still pushing into the Asian plate. It's still driving north. As a result, the Himalayas are still rising by a few millimeters to a centimeter every year. And that's why the entire Himalayan region is so seismically active. We are living in a slow-motion car crash.
Wow. Okay, so we've covered the theory, we've covered the history. Now we get to the part that really separates the casual learners from the UPSC rank holders. Section 6, PYQ linkage.
This is where we connect all the dots. It's not enough to know the story. You need to see how UPSC asks about this in the mains exam. You need to know how to structure the answer.
Let's start with link 1. This is from 2014 General Studies Paper 1, question 17. The question was, why are the world's fold mountain systems located along the margins of continents? Bring out the association between the global distribution of fold mountains and the earthquakes and volcanoes.
Okay, this is a classic plate tectonics question. It's 2 parts. A student needs to explicitly link fold mountains to convergent boundaries. So for the first part of the answer, why the margins of continents? The answer is simple, because that's where the plates collide. When an oceanic plate, like the Nazca plate, crashes into a continental plate, like the South American plate, The edge of the continental margin gets compressed and crumpled up. That crumpling forms the fold mountains, in this case the Andes.
So the mountains are basically the bumper of the car that got smashed in the collision.
That's a perfect analogy, exactly. Now for the second part, the association. You have to explain what I call the triad of tectonics. The same collision process that folds the mountains also forces the denser oceanic plate down into the mantle. That's subduction. And that subduction process causes three things to happen in the same place. One, the friction and stress of the plates grinding against each other causes earthquakes. Two, the subducted plate gets heated and melts, creating magma that rises to the surface to form a chain of volcanoes. Three, and the compression itself forms the fold mountains. So you have to show in your answer that these three things, mountains, quakes, and volcanoes, are not just coincidentally in the same place, they are all symptoms of the same single underlying cause. Plate convergence at a subduction zone.
Excellent breakdown. Okay, link 2. This one is from 2020 GS1, question 4. Discuss the geophysical characteristics of Circum-Pacific zone.
Right. This is another way of asking about the Ring of Fire, but if you just write, the Ring of Fire has a lot of volcanoes and earthquakes, you're going to get very average marks.
They want the geophysical characteristics. The why?
Precisely. You need to use the terminology we've just discussed. You must mention the Pacific Plate. You have to state that it is almost entirely surrounded by convergent boundaries. You have to talk about the deep oceanic trenches like the Mariana Trench, which are a key feature. You mention the chains of volcanic island arcs on one side and volcanic continental arcs on the other. The core geophysical characteristic is that this entire zone is a region of active, ongoing subduction. That's the key concept.
Got it. Okay, link 3. Back to 2014, this was question 18. Explain the formation of thousands of islands in Indonesian and Philippines archipelagos.
Now, this is where knowing your minor plates really helps you shine. This is a specific case of ocean-ocean convergence.
So not a continent hitting an ocean, but two ocean plates crashing into each other.
Exactly. For example, the Pacific Plate colliding with the Philippine Plate. When one dense oceanic plate subducts or dives under another oceanic plate, it melts in the mantle. That magma then rises up through the overlying ocean floor. It builds underwater volcanoes. Eventually, over millions of years, those volcanoes grow so large that they breach the surface of the ocean.
And the tips of those volcanoes become the islands.
Precisely. Indonesia and the Philippines are classic examples of volcanic island arcs. They are long, curved chains of volcanic islands created by the subduction of one oceanic plate beneath another.
Brilliant. Okay, final link. The freshest one we're looking at from the 2025 paper, GS1, question 16. Discuss how the changes in shape and sizes of continents and ocean basins of the planet take place due to tectonic movements of the crustal masses.
Okay, this is the big one. This is the synthesis question. It's basically asking for the entire story we just told in this deep dive.
So you have to put it all together.
You have to combine everything and structure it logically. To get top marks here, you need to break it down. First, you talk about continental drift. Explain how the breakup of Pangea changed the shapes and positions of the continents themselves. That's step one. Second, you bring in seafloor spreading. Explain how the creation of new crust at mid-ocean ridges changes the size of the ocean basins. Use the Atlantic getting wider and the Pacific getting smaller as your key examples. Second, you bring in seafloor spreading. Third, you use plate tectonics to explain how collisions, like the India-Asia collision, reshape the continents through folding and accretion, adding landmass. Second, you bring in seafloor spreading. Basically, you're explaining that the Earth is a dynamic system where the world map is constantly being redrawn by these three interconnected processes.
Wow. You know, when you break it down like that, the questions don't seem nearly as intimidating. It's just about applying the rules of the game we learned in Chapter 4.
That's the secret. The examiners aren't trying to trick you with trivia. They are testing your ability to apply the core concepts. They want to see if you can think like a geographer, to see the connections.
So let's wrap this incredible journey up. We've gone from Wegener's, almost childlike observation about a jigsaw puzzle to Hess's conveyor belt model, and finally to the modern, elegant understanding of plate tectonics.
I think the big takeaway is that the Earth is dynamic. It's alive in a geological sense. The ground isn't just shaking in an earthquake. It's part of a system that's constantly creating, moving, and recycling itself.
And before we sign off, a final reminder. We just gave you the verbal breakdown of how to approach those mains answers. But if you want the fully written model mains answers, structured perfectly for the exam, with introductions, body points, diagrams, and conclusions, you really need to join the private Telegram library.
Just DM us on the public channel to join. It is genuinely the best way to consolidate what you just heard. We know from learning science that reviewing high-quality notes right after listening boosts retention by huge margins.
And if this deep dive helped you visualize the moving Earth beneath your feet, please subscribe to the Simplified UPSC by PPP channel, and if you can, support us on Patreon. Your support literally keeps this show on the road. Or, I guess I should say, on the moving plate.
Nice one. Very good.
I try. Now, as always, here is a provocative thought to leave you with. We talked about the Indian plate crashing into Asia. We know the Himalayas are still rising. We know that the energy from that collision isn't just disappearing, it's building up in the rocks.
Right. The stress is accumulating.
We are living on an active crash zone. The process hasn't stopped. The plates are still grinding against each other, and that strain energy is being stored in the rocks beneath the Himalayas right now as we speak. So what does that mean for the future seismicity of the region? And maybe more importantly, are we as a society prepared for the inevitable eventual release of that energy?
That is a very sobering thought. The stress is accumulating every single day, year after year.
Something to mull over until the next deep dive. Stay curious, stay ground well, as grounded as you can be on a moving plate. See you next time.